Welcome back, everyone, to the Deep Dive. This time, we're taking a look at something pretty fundamental to space exploration, escape velocity. We've got a great resource from Open Educational Resources and open source physics at Singapore to help guide us today.
Sounds good.
Yeah, it's got a ton of equations, even simulations. So
Oh, cool.
we'll really be able to,
Yeah.
wrap our heads around this.
Awesome.
Ever look up at the moon and wonder why it's so dry and desolate compared to Earth with its oceans?
Oh, yeah, for sure.
I know I have. Well, turns out escape velocity might be the key to sort of unlocking that mystery.
Well, what's really interesting about escape velocity is that it's all about overcoming gravity.
Right.
It's the speed that an object needs to reach to break free from the gravitational pull of a planet or moon.
Okay.
Think of it as like the cosmic speed limit. You hit it, and you're free to explore the universe.
So what goes up doesn't necessarily have to come down.
It's exactly.
There's a chance it could just keep going.
Yeah, but to escape a planet's gravity, an object needs a lot of energy. It's like almost like trying to roll a ball uphill, right?
Right.
You need enough force to reach the top and then keep going.
Right.
In physics terms, we're talking about kinetic energy overcoming the gravitational potential energy that's holding it down.
Okay, I'm with you. So our source actually gives us like a formula to calculate this escape velocity.
Okay.
And it factors in things like the gravitational constant, the mass of the planet, and its radius.
Right.
So it's not just about how big a planet is, but also how dense it is.
Precisely. And when you apply that formula to Earth, the escape velocity is it's pretty mind-blowing. It's 1.12 times 10 to the fourth meters per second.
Whoa.
That's over 25,000 miles per hour.
That is incredibly fast. It really puts into perspective just how strong Earth's gravity is.
Yeah.
Now, what about the moon? Our source mentions that its escape velocity is much lower.
Yeah. It is significantly less. It's only about 2,400 meters per second. So about 1/5 of Earth's. And that difference is crucial to understanding why the moon is so different from our planet.
Okay, so how does escape velocity relate to the moon being a dry, barren world? I'm ready for that, aha moment.
Okay, well, imagine like water molecules on the early moon.
Okay.
If those molecules got heated up enough, they could actually reach the moon's escape velocity, which is relatively low.
Right.
Essentially, they'd be moving so fast that the moon's gravity couldn't hold them anymore and they would escape into space.
That makes sense. It's like, if you throw a ball up in the air.
Yeah.
It depends on how hard you throw it, right?
Right.
Throw it hard enough and it's gone.
Exactly.
But to figure out exactly how hot those water molecules would have to be, we need another piece of the puzzle, right?
Absolutely. We have to consider something called root mean square speed, which is a way to describe the average speed of molecules in a gas.
Okay.
The hotter the gas, the faster the molecules are zipping around, right?
Right.
And if enough of them reach that escape velocity,
Yeah.
well, say goodbye to your oceans.
Okay, so using this root mean square speed,
Yeah.
our source calculated the temperature the moon would needed for these water molecules to escape. What did they find? Something tells me it's pretty hot.
Oh, it's scorching. Calculations showed that the moon's surface would needed to be around 4.2 times 10 to the third Kelvin
Whoa.
for water molecules to escape its gravitational clutches.
So that's thousands of degrees.
Thousands of degrees.
And much hotter than even molten lava.
Yeah, think about that.
Wow. That's a scorching temperature. I mean, it makes sense, though, knowing that the moon is so incredibly dry today, like a massive desert in space. But it begs another question, though. If the moon was once that hot, what other things might have evaporated away?
That's a really good question, and it leads us to a fascinating discussion about the moon's possible past.
Right.
If water could escape its gravity, what about other volatile compounds? What might the early moon have been like? Hold that thought, because we're about to dive deeper into those mysteries right after this. It's like we're piecing together this cosmic puzzle.
Right.
We know the moon is dry now, and we know its escape velocity is much lower than Earth's.
Yeah.
So it's not a stretch to imagine a time when the moon was hot enough for not just water, but other compounds to just float away.
Okay, but wouldn't the moon have cooled down eventually?
Right.
Could some of those compounds have, returned? Or maybe been trapped later on in its history?
That's where things get really interesting.
Okay.
The early moon, we're talking billions of years ago,
Right.
was a very different place.
Yeah.
It's thought to have formed from this giant impact, a
Mm.
collision between Earth and like a Mars-sized object.
Wow.
The heat generated from that event would have been immense, creating a molten lunar surface.
Right.
So any water or volatile compounds present at that stage might have just evaporated quickly.
It's mind-boggling to picture the moon as this like molten, volatile world
Yeah.
compared to the cold gray sphere we see today.
Right.
What kinds of compounds are we talking about here?
Mm.
Besides water.
Well, think about things that evaporate easily at relatively low temperatures.
Okay.
Hydrogen, helium, these are the lightest elements, and
Got
would have
it.
been among the first to disappear. But there could have been more complex molecules, too.
Okay.
Things like methane, ammonia, even carbon dioxide.
So we're not just talking about a dry moon,
Yeah.
but potentially a moon with a completely different atmosphere, if you can even
Mm.
call it that, than what we observe now.
Exactly.
That's wild.
Yeah.
Does this mean the moon could have been more Earth-like at some point, even for a short period?
It's certainly a tantalizing possibility.
Okay.
Now, I'm not saying there were oceans and rainforests on the moon,
Right.
but the presence of these volatile compounds, even temporarily,
Yeah.
could have significantly impacted its early evolution.
Okay.
It might have had a thin, transient atmosphere, a more dynamic surface with volcanic outgassing,
All right.
maybe even temporary pools of liquid.
Wow.
It paints a very different picture from the static, airless moon we know today.
And all of this is tied back to that concept of escape velocity,
Right.
the ability of these lighter compounds to essentially break free from the moon's gravitational grasp.
Yeah.
It's almost like a filter,
Right.
determining what the moon could hold on to and what would be lost to space.
Precisely.
Hmm.
And the simulations linked in our source really help visualize this.
Oh.
You can play around with different masses and launch speeds
Okay.
to see how gravity and escape velocity work together. It's a great way to build an intuitive understanding of these concepts.
Yeah.
You can even experiment with launching things from the moon and see how much easier it is compared to Earth.
I'm definitely going to check that out.
Yeah.
Sounds like a fun way to grasp these ideas.
Yeah.
But what I'm really curious about now is what this all means for our understanding of the moon's formation and history. We've talked about the early moon, but how do scientists actually use this knowledge of escape velocity and volatile compounds to piece together the moon's story?
Well, the presence or absence of certain elements on the lunar surface provides clues. For example, the relative scarcity of volatile elements compared to Earth
Yeah.
supports the idea that the moon experienced this period of intense heating and outgassing early on.
So it's like a fingerprint. The lack of these elements tells us something about the moon's past.
Exactly. It's a bit like detective work,
Yeah.
using the evidence we have to reconstruct the sequence of events.
Right.
And escape velocity plays a key role in that reconstruction.
Okay. But even if the moon was initially super hot,
Yeah.
wouldn't it have cooled down over billions of years?
Right.
Could it have captured any of those lost volatiles back from space later on? Or maybe held on to some in its interior?
Now, those are excellent questions,
Yeah.
and they're at the forefront of lunar research today. It's unlikely the moon could recapture significant amounts of those lost volatiles,
Right.
especially the lightest ones like hydrogen and helium.
Okay.
However, there's growing evidence that water ice might exist in permanently shadowed craters at the lunar pole.
Wait, so there could be water on the moon right now,
Yeah.
hidden away in these craters?
Yeah.
But how did it get there if it was so hot in the past?
Right.
And wouldn't it evaporate even if it was in shadow?
That's the exciting part.
Okay.
This water ice likely arrived later,
Hmm.
possibly delivered by comets and asteroids impacting the lunar surface.
Okay.
And because these craters are permanently shadowed,
Right.
temperatures remain extremely low, preventing the ice from sublimating.
Sublimating.
That is, turning directly from a solid to gas.
Okay.
So even though the early moon was hot enough to lose its initial water,
Right.
it might have acquired new sources later on.
This is blowing my mind.
Yeah.
We started talking about escape velocity,
Yeah.
and now we're talking about water ice on the moon. It just shows how interconnected everything is in space.
It really does.
Yeah.
And this brings us back to a point we touched on earlier,
Okay.
the possibility of other volatile compounds besides water.
You mean things like methane and ammonia that could have been present on the early moon?
Exactly. And that leads us to a fascinating question for our listeners to ponder.
Okay.
What if those compounds weren't completely lost?
Right.
What if traces of them still exist somewhere on the moon,
Mm.
perhaps locked away in the lunar soil or beneath the surface?
Okay.
And what could that tell us about the moon's history?
Right.
And even its potential for supporting life, past or present?
Yeah, it really is amazing to think that the moon, this like seemingly barren world, might hold clues to its own past.
Hmm.
Maybe even a past with more water and other compounds than we see today.
Oh, yeah.
Really.
It really is like a humbling reminder that even in our own cosmic backyard, there's still so much we don't know.
Right.
That's the beauty of science, isn't it? There's always something new to discover.
Absolutely. And uh, this deep dive into escape velocity has really opened my eyes to just how dynamic the moon might have been in its early history.
Right.
It's not just this static, unchanging orb,
Mm.
but a place that has undergone some incredible transformations over billions of years.
And what's so fascinating is how this, like, seemingly simple concept of escape velocity
Right.
can help us unravel those transformations.
Yeah.
It's a fundamental principle that governs the behavior of, celestial objects, from planets and moons to stars and galaxies.
It's like a key that unlocks a deeper understanding of the universe.
Yeah.
We started this deep dive wondering why the moon doesn't have oceans like the Earth,
Right.
and now we're talking about a possible ancient atmosphere, hidden water ice, and even the potential for other compounds trapped beneath the lunar surface.
And that's just scratching the surface.
Oh.
Each new discovery just raises even more questions,
Right.
prompting us to dig deeper, to refine our models, and to explore new possibilities.
Yeah, our source from Open Educational Resources and Open Source Physics at Singapore has been an incredible guide,
For sure.
providing us with, equations and simulations and background information
Yeah.
to really grasp these like complex ideas.
It's dense stuff.
I especially love those interactive simulations.
Oh, yeah.
It's one thing to hear about escape velocity, but it's another to actually see it in action,
Right.
to play around with the different variables
Yeah.
and see how they affect the outcome.
Exactly.
So for our listeners who are eager to learn more, I highly recommend checking out those simulations.
Yeah. They're really cool.
They're linked in the source material, but even beyond the science, there's something truly awe-inspiring about this idea of escape velocity.
Yeah.
It represents the ability to break free from these gravitational constraints, to venture beyond the familiar
Yeah.
and explore the vast unknown.
It's a testament to human ingenuity and our relentless drive to push the boundaries of knowledge and exploration.
Right.
Think about, the Apollo missions.
Yeah.
The first human footsteps on the moon.
Right.
That was a triumph of engineering.
Yeah.
And, a profound moment in human history, made possible by understanding and harnessing the power of escape velocity.
It makes you realize that the sky is not the limit when there are footprints on the moon.
Right.
And who knows what the future holds.
Yeah.
Perhaps one day we'll use our understanding of escape velocity to journey even farther, to other planets, to other star systems.
The possibilities are truly endless. And the more we learn about the universe, the more we realize just how much more there is to learn.
Right.
So to our listeners, we encourage you to keep exploring,
Yeah.
to keep asking questions, and to never lose your sense of wonder.
Right.
The cosmos is full of mysteries just waiting to be unraveled.
Hmm.
And you might just be the one to make the next groundbreaking discovery.
Until next time, keep looking up and keep diving deep.